Hi, this is Nick Bizzani, and this is a video I've crafted from some slides that I used in the Flint, Michigan training modules that I had done under a contract with the state of Michigan to provide training modules for the city of Flint operators. This is for the 3 chemical feeds that they use, and I'm going to share this screen with you now so that we can go through this presentation. Even though this was specifically for Flint, I think it's good for all operators to understand how to do these chemicals. So this is going to be an example chemical feed calculations for the Flint operators for the phosphate, hypochlorites, and caustics that they use. This again was under the previous contract I had with the Michigan DEP. Flint, Michigan water treatment plant, of course, was directed by the US EPA to add chemicals to the incoming water that they were receiving from Detroit or the Great Lakes Water Authority prior to distributing it to their own customers in Flint. Specifically, the directive that US EPA brought against the city of Flint was that they had to add amounts of 3 chemicals so that the specific levels or goals could be met for the drinking water before it was distributed. And in general, they said they shall do this. They shall add phosphoric acid, such that the distributed water has about 3.4 milligrams per liter phosphate in it. They had to add sodium hypochlorite, such that the chlorine residuals in the system met specified requirements as at predetermined locations. The number of 12 or so locations, and they're too numerous to mention here, but they had to boost the chlorine. That's sufficient to say that. And of course, they had to add caustic soda so that they brought the pH up into a range where the hypochlorites and the phosphoric acid was going to be good for their lead and copper program. So this training tutorial instructs the Flint operating staff in the dosage calculations only. There was a lot of other training that went along with this, of course, but this is basically just how to calculate dosage for these 3 chemicals. So let's do the phosphoric acid first. We know that phosphoric acid is depicted chemically by the formula H3PO4. So in Flint, the staff adds the orthophosphate in the form of phosphoric acid to the water to inhibit the dissolution of lead and copper at the customer's tap, but also to repair the damage that was brought on by the plant startup issues in April of 2014. Now, US EPA set a required level of phosphate, not phosphoric acid, but phosphate at 3.4 milligrams per liter roughly for Flint. And remember, the water from Great Lakes Water Authority was coming in and already had about 1 milligram per liter phosphate in it. So they had to boost it from 1 up to 3.4. So phosphoric acid, as I mentioned before, was depicted chemically by the formula H3PO4. So let's dissect that chemical molecule. The amount of phosphate, the amount of PO4 in the molecule is derived by first adding the atomic weights of each element together to calculate a total formula weight. So let's do that. We see we got 3 hydrogens, and the atomic weight of hydrogen is 1. So 3 times 1 equals 3. So that would be the contribution that hydrogen would make to the overall molecule. So we get 3 from the hydrogen. The phosphorus would be 1 times 31, or 31 total. So now we've got 3 for the hydrogen, 31 for the phosphorus. And we notice that there are 4 oxygens, and each oxygen is worth 16 for an atomic weight. So 4 times 16 would be 64. So when I add those 3 up, I come up with 98 total formula weight. The weight of phosphate then is divided by the total weight of the phosphoric acid to get a percent available PO4 in the molecule itself. So the PO4 then is 64 plus 31, or 95. And so if I take the 95 and divide it by the total formula weight of 98, I come up with about 97%. So in other words, of this phosphoric acid molecule that we're adding to the water, 97% of it is phosphate, or is phosphoric acid in the available phosphate. So you need to know the strength and density of the acid that was shipped to the plant. And at the time this module was created, the information that we found on the container label stated that this product was 75%. And of course, that can always change. You know, when you get material in, you always got to check the bill of lading to determine what you're getting from the manufacturer. And they stated that the density of this product, as shown, was 13.14 pounds per gallon. That came from the specific gravity of 1.5755 times 8.34. So the dosage control example for phosphate feed for the plant operators went like this. Suppose the incoming water from Great Lakes Water Authority has a phosphate level of 1 milligram per liter. And Flint desires to boost the phosphate level to, say, the 3.4 milligrams per liter phosphate by adding sufficient phosphoric acid to a flow of 14 mgd to accomplish this task. So they need to know how many milliliters per minute of the acid they're going to feed to get up to 3.4 milligrams per liter phosphate in the 14 mgd that's coming in from Great Lakes Water Authority. So it goes like this. The needed feed amount would be the 3.4 that they need to get to, minus the one that's already in the water from Detroit, or about 2.4 milligrams per liter phosphate must be added. The 2.4 milligrams per liter times 8.34 times 14 would show that they would need 280.2 pounds per day of phosphate needed. But they don't have phosphate. They've got phosphoric acid. So they're going to need to throw in those percentages that we just talked about. We're going to take that 280.2 pounds per day of phosphate needed and divide it by the 75% strength of the acid and the 97% of the phosphate out of the total molecule of phosphoric acid. So they're going to need to feed 385.15 pounds per day of acid to the water coming in. So how many milliliters per minute does that work out to? What should they set their chemical feeders at if they have to feed 385.15 pounds per day of acid? They're going to take that 385.15, change it to gallons by dividing by the pounds per gallon weight of 13.14, then change those gallons into milliliters by multiplying 3,785 times the total amount of gallons. But it's going to come out to 110,944, approximately 110,944 milliliters per day acid that has to be fed. I'm going to take that milliliters per day and divide it by the 1440 minutes. That comes out to approximately 77 milliliters per minute being fed. And that's what the operator would do. They would go to the feeders and set that. And let's take a look at some of the pictures we have from the feeders here. On the left, you see the Hawk Series 500 phosphate analyzer that takes the water in from Detroit and analyzes it for phosphate, so they know if they're at 1 milligram per liter or not, roughly. In the middle, the bottom picture is the CS2 panel that shows the flow rate in the upper right-hand corner. And I think I got that highlighted there. Yeah, circle around it, showing the flow rate coming in, so they know if it's 14 or not. And then the feeders at the top are the ones that they have to set for 77 milliliters per minute. They normally one lead and the other lag. And then on the right, you can see the operator using the 1,000 milliliter calibration column, fills it up, times it for a minute to see how long it takes to drop out the 77 milliliters. What are you actually getting at? So you can do that for 3 units of 77, say, and determine how long it takes. Or you can do it for 1 minute and see how many milliliters you get. Either way, that's the way to set your feeders. So that's the phosphate. Let's now go to sodium hypochlorite. Now the sodium hypochlorite is depicted chemically by the formula NaOCl. It's a liquid. Liquid chemical contains chlorine. So they're not using chlorine gas, they're using a liquid chemical that contains chlorine. So just like the phosphate, which was part of the phosphoric acid, this is chlorine, which is part of the hypochlorite. So we got to figure that percentage out. Of course, Flint staff adds sodium hypochlorite to the water to boost the level of chlorine residual coming in from Great Lakes Water Authority and to maintain the chlorine residual in all parts of their distribution system. And they have goals for different parts of the system. Like I said, it's very involved, and I can't get into all of it here right now. But we know that hypo, of course, is also used in the water treatment business as a primary disinfectant. But here we're using it to boost the system chlorine. Now, the strength of the sodium hypochlorite that is supplied to Flint can vary anywhere from 5 to 20%. We know that hypochlorite is most stable at 6% and will tend to decay over time. You get off-gassing, a loss of strength can occur at higher percentages. And then, of course, the higher temperatures can do that too. They got a recent shipment and it had about 18% strength to it. But the way they get around that is to buy smaller quantities of it more often. And so they don't have too much of a problem with off-gassing or losing strength that way. If you buy it often, you can do that. So let's look at 2 dosage control examples for hypochlorite. This is always a good idea. I think they have more than one way to skin the cat here, as I've mentioned in other videos. If you can calculate the dosage 2 different ways and come up with the same numbers, then you know you're on track. One is a check on the other. So let's say this. I'm going to do this over 2 slides. The hypochlorite solution at Flint was 18% when we did this slide presentation. So we know this about the concentration of the hypochlorite at Flint. It's 18%. It must contain 180 milligrams of chlorine per milliliter of solution. We also know this. We know that 1 gallon of the hypochlorite solution will provide 1.5 pounds of chlorine. And also we know this. 0.6 gallons of the solution will transfer about 1 pound of chlorine to it, in it. So you got 3 different ways of looking at that concentration. As long as you know it's 18%, you can claim all 3 of those factors and use 1 or more of them in your calculations. So let's say we have this situation occurring. We have this information about the hypochlorite, it's 18%, so we know those 3 things. We're going to work 2 examples of dosage on the next page, given that the incoming Great Lakes Water Authority flow was at 14 mgd, and we were wanting to dose the water with an additional 0.3 milligrams per liter of chlorine. How many milliliters per minute of hypo solution would I feed? Now, if you want to work this out for yourself and give it a try, go ahead and stop the video now and work it out with pencil and paper and your calculator, and then come back to the video and I'll show you the answers. And I'm going to do it 2 different ways. Okay, here's 2 example dosage calculations from the previous slide. On the left here, I'm looking at calculating the feed amount in pounds for pure chlorine that I would need. If I had pure chlorine, how much would I feed? Well, all I'm feeding is 0.3 milligram per liter times 8.34 times the 14. It tells me I would need to feed 35 pounds per day of chlorine. Pretty simple, standard dosage problem. But of course, I don't have pure chlorine, gaseous chlorine there. I've got hypochlorite solution, so I've got to do a little bit more math. So let's work through that. So the next thing I'm going to do is calculate the feed amount in pounds for 18% hypo. How much would I have to feed? Well, if I need 35 pounds per day of chlorine, and each gallon of the hypo provides 1.5 pounds of chlorine, if I work that calculation through, I'd come up with 23.3 gallons of hypo solution would be needed to produce the 35 pounds per day of chlorine. Now then that makes it simple. If I know how many gallons I have to feed in a day, then I can work it out the milliliters per minute, and that's what I'm going to do next. Calculate the milliliters per minute hypo solution needed. I'm going to take the 23.3 gallons per day, multiply that by 3,785 to change gallons to milliliters, and divide by 1,440 minutes to change that day to minutes. And I come up with an answer of about 61.2 milliliters per minute solution needed. So I would go set the feeders for the 61.2. All right, let's try it a different way. Let's see if I come up with the exact, or with the same number of around 61 milliliters per minute by doing it a second way. Let's take another piece of that information that we had. I'm going to take the flow rate itself first. I'm going to take that 14 mgd and change it to liters treated per minute. In other words, the water flow coming in from Detroit, from Great Lakes Water Authority, of 14 mgd, we'll change it to liters per minute by dividing by 1440 and multiplying that by 3.785 liters per gallon. And I'm changing that 14 million then to 36,798.6 liters of treated water per minute. Okay, I'm going to express the concentration of hypo as milligrams chlorine per milliliter. And we saw from the previous page that 18% hypo, if I multiply that by 10, I'd come up with 180 milligrams of chlorine for every milliliter of hypo. So now I know that every milliliter of hypo I feed to the water, I'm feeding 180 milligrams of chlorine. So now maybe you can guess it should be pretty easy to figure out how many milligrams per liter I'm going to get because I've changed the flow rate to liters per minute. Let's see how we go from there. I'm going to calculate the milligrams per minute of chlorine needed. Take the 0.3 milligrams per liter chlorine needed times the 36,798.6 liters treated per minute. I'm going to get 11,039.6 milligrams per minute of chlorine being needed. And when I work that through, I take the 11,039.6 milligrams of chlorine needed, multiply by the fact that 1 milliliter will provide 180. So how many milliliters do I need? If each one I put in is 180, and I've got to get up to 11,039, I'm going to divide one by the other, come up with 61.3 milliliters per minute solution needed, which matches pretty well the 61.2 on the left-hand side. So there were 2 ways to do the calculation. Each of them can act as a check on the other. The operator is pretty confident that he's got the right answer. He can now go set his machines. Okay, so the last chemical here briefly is sodium hydroxide, depicted chemically by the formula NaOH. Caustic soda is used by Flint to adjust the pH and alkalinity upwards. It's added to the GLEWA supply, the Great Lakes Water Authority supply, to assist in the corrosion control program. So operators are bringing the pH upwards to a range in which the orthophosphate is going to work best. We know that maintaining a pH in the specified range is going to ensure that Flint water has the least chance to dissolve more lead. So that's where we want to be. But generally that's going to be around 7.4 pH or 7.5, somewhere in there. We know we don't want to go too high. In the water treatment industry, adjustment of pH is usually accomplished by addition of a chemical to bring the water up to or down to a specified pH range, which is optimal for regulatory compliance and also process control. For example, at a conventional water treatment plant, we need to keep the coagulation pH low enough to make floc and to take out TOC, but we need to keep it high enough to not get us in trouble with lead and copper. So that's a balancing act. Sometimes we might add an acid, sometimes we might add caustic as a base, depending on which way we've got to go. So the Flint staff, of course, does not need to pre-treat the water. They're not a full-scale treatment plant. They're taking finished water already and boosting up some of the levels. So they're going to add caustic just to bring the pH up a little bit to get it in that range that's ideal for them alone. So they're meeting a range. I should also point out if they're using orthophosphate, which they are, of course, the finished pH should not get too close to 7.8. So they want to be somewhere around 7.4, 7.5, 7.6. So they're, rather than adding a dosage of caustic like you would with the orthophosphate, the known dosage, you want to get up to a certain range. So you're going to add enough corrosion control, or rather caustic soda, to get up to a certain range of pH. Then later on, you can figure out what dosage that is so you can set your feed pumps. So let's look at it this way. Caustic strength is typically obtained in the 20 to 50% range, and the product is often purchased at 20% in order to minimize freezing. And I'm going to show you a slide that will show you why that's done at 20%. Specific gravity of a recent 20% caustic solution that they got in was at 1.22. So the solution weighed 10.17 pounds per gallon. Let's look at this chart, which is a sodium hydroxide freezing point chart. It's pretty wild. On the left, I've given you some chemical information about the sodium hydroxide, not too important right now. It was important for some other modules that I did, so that's why I put it here. But look at this chart on the right. On the bottom, you see percent sodium hydroxide going from 0 to 80%. On the left-hand column going up is degrees Fahrenheit. On the right would be degrees centigrade, either way. But look, it's not a linear graph. It's a wildly snaking around graphic that shows you, for example, that at 20%, you can see on the bottom chart there, about a third of the way along, it's 20%. It won't freeze up until you get as low as 20 degrees, minus 20 degrees Fahrenheit. But if you concentrate it to 50%, you'll see that it'll freeze at around 50 degrees Fahrenheit. So that's the conundrum with feeding caustic. If you get it strong enough to where you don't have to use that much of it, it's going to turn into slush because it freezes at a higher temperature. If you change it down to 20%, it's not going to freeze on you most of the time, but then you got to feed a lot more of it because it's weaker. So you got to pick your poison here. Poison they picked, of course, was to get it in at 20%. But here's a 50% caustic dosage example. Rather than target a dosage of milligrams per liter, as I was mentioning, caustic is fed to meet a target pH. So let's do an example. Let's say it took 3 milligrams per liter of pure caustic, now pure chemical, not the 50%, but pure chemical to meet the target pH. I'm sorry, this is a 20% example, not a 50. How many milliliters per minute of the 20% caustic should be fed? So the chemical weighs 12.17 pounds per gallon. The scale is provided to record weight loss. Pounds per day pure caustic was 3 milligrams per liter times 14 mgd times 8.34, or 350 pounds per day pure caustic being fed. If I work that out for the 20%, if I needed 350 pounds of pure caustic per day, I divide that by 0.2, I'm going to get 1,750 pounds per day of the 20% caustic I need. So I got to feed that much more of it. For the 1,750 pounds per day, 20% caustic, divided by the fact that it weighs 10.17 pounds per gallon, it means I would have to feed 172 gallons per day of this product. So now I can change that into milliliters per minute by taking the 172, multiplying by 3,785 milliliters per gallon, just like I did with the other chemicals, and dividing it by the 1,440 minutes in a day, and I come up with 452 milliliters per minute, 20%. So I should probably correct that before you get all confused. There, 20% caustic is my fault. So there we go. Make a note of that. You might want to take a little snapshot of that thing. So in all cases, we changed the dosage feed. We got into the point where we got gallons per day needed. We change that gallons to milliliters per minute by using the 3.785 and the 1440 minutes. That way we know what set the machine at, and we can go up to the machine, the feed machine, fill the calibration column to the 1,000 milliliter mark and let it go for a minute or 2 minutes or 3 minutes and figure out how many milliliters per minute we're actually feeding and adjust accordingly. So that concludes the Flint chemical dosage training video. If you desire to refresh yourself on some of the other water treatment math topics that I've produced, you can see a couple of links being scrolling up here at this point. You can click on either one of them. It'll bring you some of the other modules, and I hope that this was useful for you. And with that, we're going to stop sharing, and we're going to conclude our video. Thank you for your attention. I hope this helped you.